Hello, this is Mr. Gilmore with the 11.7 Similarity and Area lesson. Our question today is simple. When we scale a figure, what happens to the areas between the two scaled figures? Let's dive into this question. So recall that when we talk about scaling a figure, it means that there exists this scale factor, we'll call the scale factor K, such that if we are given the figure, every single dimension of that figure is then multiplied by K. And that means all measures, such as the sides, altitudes, radii, whatever it is, they're all multiplied by the scale factor K. What we're going to do is an experiment, a geometrical experiment of the sort, where I'm going to give you a number of different figures in which we're going to scale them by some scale factor K, and we're going to observe what the area results are. Once we get through our experiment, we'll generalize this and use our generalization, basically this generalization approach in several examples. Let's dive into our first of our experiments. Let's say I give you a square. That first square has a side length of 1, and we scale it to a side length of 3. So our scale factor K is equal to 3. Let's observe what happens to the area. So the area of our first square, we simply just do 1 squared, is 1. The area of our second square, we do the side length square, which is 3 squared, we're 9. Our goal then is to see, well, what's the relationship of this? So notice that our scale factor, our K, is 3, but the area to go from one to the other got multiplied by 9. I wonder what the relationship between our scale factor 3 and being multiplied by what our product was here to go from the first to the second, what the relationship is there. Let's dive into a second and see if we observe a pattern. So our second is then of a rectangle. We can find the area of the rectangle by just finding the product of its dimensions. So the first rectangle has an area of 4 times 2, or an area of 8. Our second rectangle has an area of 2. It was scaled by 1/2. So our scale factor is 1/2. But what did we do to multiply from our first to get to the second? We multiply by 1/4. Let's observe. Do we see a pattern yet between our scale factor and the area of how it's being scaled? Let's do that with a circle. We're going to scale it with now a scale factor of 1/4. So the area of our first circle here is then 16 pi, right? It's radius squared times pi. The area of our second circle is just simply 1 pi, right? Which is then 1 squared, or just simply pi. So our scale factor is 1/4, but what did we multiply by? We multiplied by 1/16. Are we beginning to observe a pattern? Let's do one more, and then we'll see the generalization of this. Let's do the scale of a triangle. The area of a triangle is 1/2 base times height. So the area of our first would be 1/2 2 times 3, or an area of just simply 3. And let's do the area of our second. 1/2 base times height would give us an area of 12. 1/2 of 4 times 6. Well, our scale factor was a length, or the measure of 2, but what did we multiply to get from our first area to our second? We multiplied by 4. And hopefully you've now been seeing the pattern here, that when we scale the area, or so when we scale a figure, the area gets scaled not by K, but by K squared. Think about that. In every single one of our examples, the given K that we had, simply squaring it, resulted in the value in which we multiplied from the first area to get to the second. So let's generalize this now and take a look at how we can actually use this generalization for any scalable figure. So if we generalize this, let's consider then A representing our pre-scale area, or the original area of our figure before we scale it. Let's let K be the scale factor as we scale that given figure with area A. What we're going to find then is that the post-scale area of our figure, we'll call that A prime. A prime is equal to K squared times A. Or we can relate that the ratio of our post-scale to our pre-scale is in fact the ratio of K squared. So we can use this fact here to actually then help us answer a few questions. Because if we're given a scale factor in any one of the areas, a pre-scale or the post-scale, we can work towards finding the other area, whether it's finding the post-scale or pre-scale area using the given scale factor. So let's start with a very simple problem. A figure is scaled by the factor 7, which means we have a scale factor K of 7. Its pre-scale area is 2. Pre-scale means it's just simply A. What is the post-scale area, meaning what would be A prime? Well, we just saw the relationship that A prime has with A is simply k squared times a. Let's plug in what we know. Our k is 7, so we're doing 7 squared, times a, which is 2. So 7 squared is 49, times 2. Our post-scale area is 98. And that is what our area would then be if we scale our given figure, whatever it may be, which has some sort of area of 2. Our post-scale area would then have to be 98 because it is scaled by k squared. Let's take a look at another problem. We want to we find ourselves given a figure that is being scaled. Its pre-scale area, we're already told, has an area of 800. Our goal is to find out again what the post-scale area is. But notice that we weren't directly given the scale factor. We have to recall to find the scale factor, we simply just need to find a ratio of corresponding sides. Since we're going from our first to a second, that means our scale factor would have to be the second divided by the first. Or in other words, we're going to have 16 divided by 20. In other words, our scale factor is a matter of 4/5. Now we go back to our original equation, which is our scale factor a prime is equal to k squared times our original area a. So we're taking 4/5 squared and multiplying that by 800. 4/5 squared, we can square the numerator and the denominator. That gives us 16/25. Multiplying 800 by 16 and divided by 25, we get our post-scale area to be 512. Now, so we can see that our area, even though that our lengths are multiplied by k, our area is going to be multiplied by k squared. Our last example would actually be kind of working backward from, given both the prescale and post-scale area, let's find the value of our scale factor. So let's say we have a figure that's being scaled, and we're given both the prescale area and the post-scale area. That means we have a is 12 and a prime is 144. The question they're asking us is, what is k? So we can figure this out simply by using, again, our equation, or really we're going to be using our altered version of our equation, which looks a bit like this. We have k squared is equal to a prime over a. Let's plug in what we know. A prime is our value, our area of 144. A is an area of 12. We can then simplify this. 144 divided by 12 is simply 12. We can take the square root of both sides to get k by itself. Simplify the square root of 12. 2 comes on the outside, and then a factor of 3 gets stuck on the radical. And there we have it, our scale factor, 2 root 3. So when you dive over into the worksheet 11.7 and take a look at looking at similarity and area, you're going to find that we'll start off our adventure similar to what we saw here in the beginning of our lesson, which is just investigating again with areas, where if I give you a figures being scaled, you find the area of both and then do a generalization of how do we, or what do we multiply the first area by to get to the second area. And we'll notice then that pattern again is that the multiplication, that factor you multiply by, is in fact the square of the scale factor. That's going to be the number you're multiplied by. So be sure again to take a look at that 11.7 worksheet. If you do have any questions, do not hesitate to email me. With that, be good and do good.